Okay, so last class, we talked about the best fit subspace problem. Right, and we had the sequence of reductions which helped us talk about the question, right? We said minimizing error was essentially the same as maximizing the variance. Okay, and we also had this very important definition of principal singular vectors, right? Of singular vectors and principal components. Okay. And finally, we also had this idea that, excuse me, if you could find a single PC, then you could potentially find the next one by kind of trying to solve the same problem again on a slightly different kind of data set, right? So we said span of first two PCs solves the best fit subspace. Okay, so today what I want to do is kind of review this last step once. Why does looking at the span of the first to solve the problem? And then we are going to kind of, maybe start talking about a different looking problem at least. And this is the low rank approximation problem. So we'll talk about this question, and then we'll talk about one of the most important tools in linear algebra and in optimization called singular value decomposition. And finally, we'll talk about how to actually solve the computational question. So until here, we'll only be kind of, punting the problem down the line, rephrasing it, making other things, but it'll still be progress because at the end, we'll have a very nice and important algorithm, okay? So just to, and also as a reminder, say assignment 2 is due on Wednesday. Okay, so do keep that in mind. All right. Okay, so just to recap, if we had a matrix, and we have a data set really, x1, x2, and so on. We had the error notion for any subspace, which was the look at each data point, how far point from this span, from the subspace that I'm looking at. Okay, and then we had the variance term, which was just how much of each vector was actually captured within the subspace. Okay. And we said minimizing error is equivalent to maximizing variance. Right, and this was the best fit subspace problem. Okay, and we also had the singular vectors. So the right singular vectors, if v1 through vi minus 1 are singular vectors, then Vi is something which maximizes the length of X times V subject to the length being 1 and it being perpendicular to all the other directions. Okay. And the last thing that we talked about was this theorem that span of V1, V2 solves the best fit subspace problem for K equals 2. Okay. So this was the last thing that we talked about. And the reason we said was, so the main idea of the proof was take any other two-dimensional subspace. You have some other two-dimensional subspace T, which someone says, okay, this is, the span of V1, V2 is not the best. T does better, right? We said, okay, if this T does better, then I can do an argument like this. So this is my S, and V1 is some vector in the same space. I can pick an orthonormal basis for T where the vectors, the first vector is perpendicular to V1. Okay. So this was the most important part of the proof. There exists an orthonormal basis W1, W2 of T where W1 is perpendicular to V1. Okay. And once we had that, we had to use kind of Pythagoras' theorem a couple of times. And we also had this statement. Right, so this score of T, you can actually compute by looking at the length of X multiplied with W1 and looking at the length of X multiplied with W2. Okay, this is true for any orthonormal basis. And in particular, it should be true for the special basis that I'm picking. Right, in the same way, we also should have where S is the span of first two principal components. Okay, now we are good because we can actually compare these two things term by term, right? So by definition of the first principal component, the length of xw1 should be less than or equal to the length of x times v1, right? It was the vector which had the maximum length of x times v1 among all unit vectors. And by the definition of v2, xw2 should be at most x times v1, right? And this is true because w2 is perpendicular to v1, right? I should say this is w2. Right, W2 is perpendicular to V1. Okay, that's how we chose it. Okay, so this implies that the score of T is at most the score of S. All right, any questions about this proof? Okay, so I mean, you can see that we are using Pythagoras' theorem again and again, and that's partly why this whole thing only works for the sum of squares of the errors rather than sum of the errors. Okay, so that's what I wanted to say about the proof, and kind of almost the same argument generalizes to higher K. I won't do it for us. And in general, span of V1, V3 up to Vk solves the best fit subspace problem for K. Okay. So someone gave me a data set and said, okay, here's K. I want you to find the best fit subspace for this K. I just have to compute the first K principal components, and that will solve the problem. All right. And I mean, the proof of this is kind of just an extension of what we did for 2. You have to use induction, and you will do this in the next assignment as a homework. Okay. All right, so that's what I wanted to say about principal components. They'll come back again pretty soon. But before that, let me talk about a seemingly different question. Okay. So far we've been thinking of data sets as, sequence of points. You have x1, x2, x3, xn, and so on, right? Now we're going to not look at the individual points as much, but really as everything put together as a matrix given to us. Okay. And this specific problem about matrices we're going to study is called lower rank approximation. Right? And the high level idea of the problem is the following. There's a question, why can we claim W2 is perpendicular to V1? So there are actually many basis vectors that we can choose. And we're just saying that there is at least one basis, one orthonormal basis for T, where I can choose W2 is perpendicular to V1. Right? If you look at this picture, now someone might say, I don't want to use that basis. I can also use a different basis, something like this. And here, W2 is not perpendicular to V1 potentially, but all we are saying is I'm just picking among all the available basis vectors, I'm picking one where W2 is perpendicular to V1. If you want to find out how to do it, you can project V1 onto the thing, choose that as first direction, and then the perpendicular one will be perpendicular to V1. Okay. All right, it's a nice trick to keep in mind that you can choose a suitable basis to make your analysis easier. Okay. All right. Now, what is a low rank approximation problem? As far as problems go, I think this is one of the most important ones within data analysis. So you're given some matrix. Okay. Imagine it has n rows and d columns. And our goal is to approximate this matrix by a simpler matrix. Okay. You can imagine scenarios where this matrix is very complicated, maybe too cumbersome to store, too cumbersome to do operations on. So you want to approximate it by some kind of simple matrix, right? What does it, we have to decide two things. If you're asking such a question, what's the first thing we need to decide? Well, we need to understand or formulate what simple means, right? It's our choice. You had to come up with, if you are the person who's trying to figure out what the right model is, then you should ask yourselves, what does simple mean? What notion of simplicity would suit my application, make sense statistically, and also make sense as something that I can solve computationally. Okay. And then, of course, what's another question that you have to answer first to make this kind of quantitative and precise? Any suggestions? Yeah. Exactly, right? So you have to decide, what does approximate? Right, you have to decide kind of, what is your space of sort of matrices that you're going to look for, and what is a good matrix? What's a score that you're, what's a good score, and so on. Okay. And there are various notions of simplicity that people have studied, like, sparse matrices, meaning, there are not that many non-zero entries, discrete matrices, meaning the numbers are somehow have finite precision, and so on. But by far, the most useful and important one corresponds to this notion where simple just means it's a low rank matrix. Think of low as being something like 20 or 30, so very small, right? Okay. And in the end, I'll tell you why this low rank thing, it sounds like a very simplistic thing, its impact, and that in real world, you do see very low rank things. Okay. So recall that the rank of a matrix is basically, there are various definitions, is the dimension of the span of the columns of the matrix. It's also the dimension of the span of the rows of the matrix. Okay. And if you want an operational definition, then you can basically, a matrix X has rank R only if you have your matrix X. I can write it as a product of two matrices, basically kind of factorization. Can write it as a product of two matrices like this. Okay, X has rank R means I can write it as a product of two matrices where one is only n by R and the other is R by D. Okay, if I tell you R is like 2 or 3, then you're saying you might have a huge matrix, 100,000 by 10,000, but I'm writing it as a product of two small matrices. Okay. All right. So, you might wonder, why study rank as a notion of simplicity? Why is it a good notion to study? Well, there are very good reasons from probabilistic models and there are various nice probabilistic and statistical models which kind of lead to data that you can naturally assume is low rank or at least close to being low rank. Okay. You can imagine, maybe it's some kind of factors, right? If you think of each rank as, saying some factor that's important, maybe there are only a few factors, and somehow that determines the rank. Okay. Okay, that seems, maybe if you told me, I might accept it. But why is it even a simple notion? Is it a simpler class of matrices? There's one easy way to see why it's simple. Can anyone tell me why? If I tell you a rank 2 matrix I want to say rank 2 matrix is much simpler than a rank 1000 matrix, even if the final dimension is the same. In what sense is one simpler than the other? Think computationally. Yeah. Right. You can actually, if you're trying to multiply this matrix with something, it's much faster if you have a low rank factorization, right? Or even before that, think of representation. Okay. If I have to store a n by d matrix, right? You need n times d memory, at least that many bits. And if your n is like 500,000, d is like 20,000, that's already like 10 gigs of RAM. Okay. Whereas to store a n by d rank R matrix, how many numbers do you need? I mean, you can reconstruct it later. You're not going to store X exactly, but you'll store some representation. You'll say, okay, if you want at the ijth entry, here it is, right? Some kind of compression. How many entries do you need? Yeah, so we only need to store these factors, right? So I only need to store n times R plus R times D, which is basically n plus D times R. Okay. Much more manageable compared to n times D if R is small. All right. And, okay, so maybe as a further example, let's say I have a matrix where everything is proportional, like maybe this is 0.9 times U, maybe the first one is U, the next one is 2 times U, and so on. What's the rank of this matrix? Its rank is 1, right? Because every row is proportional to U. So the span of the columns is 1 dimension. Okay. On the other hand, let's say I take the identity matrix. N by n. On the diagonals, I have 1, and the off diagonals are 0. Right? This is the identity matrix. What's the rank of the identity matrix? N. It's full rank, right? Okay. Now, so at least we have some reason to believe that low rank is a good notion. It is a simpler rank. Being small leads to simple matrices, and why it also arises naturally in various probabilistic and statistical models. This is not something that we're going to cover, but at least computationally it makes sense. Okay. And I should also say the other point that was pointed out was X is rank R. To compute X times some vector, let's say V, usually would take how much time? You would have to multiply every row like this, right? That's going to be n times d time, right? So to compute each cell would involve multiplying this row with this row with vector V, so would take n times d time. Okay. On the other hand, if X is of rank R and I have a small rank factorization, how can you compute it? You would use associativity, right? You wouldn't multiply like, these two matrices and then multiply with the vector, but you'd first do the vector matrix multiplication and then kind of propagate it, right? This is something that we saw earlier also. It's an important trick, and it will show up later too. So you would basically compute it something like this. Right? So first multiply the R by D matrix with the D-dimensional vector. Let me try it. Okay. So how much time would you need to compute this? You would need RD. And then to compute the next one, you would need N times R. Okay. So once again, you have a lot of savings. Okay. So computationally, it gives you a lot of savings. And statistically, it's a good model. So it's a good thing to work with. All right. Okay. So that answers our first question. What does simple mean? But how about approximation? What would it mean to approximate? What's a good way to approximate? So you have the matrix X, and you're trying to approximate it with, a low rank matrix or some other notion of simplicity. Under some other notion of simplicity, a simpler matrix X, let's say X tilde. You have various kinds of loss functions you can define, and by and large, the most used one is the squared loss. Okay, so we'll again think of the squared error. Really the RMSE, root mean squared error. And it basically says, look at all the entries. For every entry, look at the corresponding entry. What's the error there? Okay. And then you take the square root so that everything is up to scale. Okay. And there's a notation for it. This is denoted, it's important enough that it has a name. It's called the Frobenius norm of a matrix. If I have any matrix A, then its Frobenius norm is basically the square root of the sum of squares of the matrix. Is the analog of the length of a vector, but for matrices. It's the same thing, but for matrices, it has a different name because of the history and some other properties that we'll talk about. Okay, so now we are ready to formulate our computational question, right? So what's the question? Someone gave us, I'll call this the low rank approximation problem. This is one of them. As I said, you can change the notion of approximation, but this is kind of the most studied. So let's stick with the most studied one. So the input is some matrix X, which is N by D. All right. And some number K. K could be 10, 20 or something like that. And your goal is to compute this X tilde to minimize and you want the X tilde of rank at most k. Okay. Among all matrices x tilde of rank at most k, find me one which minimizes the root mean squared error or the Frobenius norm error from x. Okay. Any questions? All right. Okay, let me describe one application of this problem to maybe some of you have already heard about it. At some point long ago, there was this thing called the Netflix challenge. Do you know what it was? Have you heard of it before? Anyway, so it made many years ago when Netflix was just coming out. They posed this challenge as like kind of, some kind of benchmarking question. And the problem that they asked was the following. They said, we're going to make public the following data, which is, I have the movie ratings of 500,000 users. Okay. And among, roughly 17K movies. All right. And if you multiply it, it's a lot of entries. And if you imagine each user, not every user rates every movie, right? Even a person like me hasn't seen every 17,000 movies. Okay, so maybe I saw some movie, it's 4, I rated 5, something else I rate 1, something else I rate 0, and so on. The stars are meant to signify missing entries. I haven't given a rating for that movie, and their goal, more or less, is to try and figure out what's my potential ranking or rating for the missing entries, right? Because they want to use that for recommendations. If they could guess what the missing star entries are, then they can suggest these are the top movies based on your preferences. These are the ones that you might like. Go check them out. All right. It's also called matrix completion problem because you have a matrix with some missing entries, and your goal is to complete the missing entries in some way. Okay. And in this huge matrix, 500,000 by 17,000. Netflix really released the ratings of about 100 million entries. Okay. So meaning this is roughly 1% of all possible entries. Okay. I said, here's a matrix, this is for public, you can download it. And you see 1% of all possible entries. 1% is, if you think of the number of movies there's 17,000. So they're saying that for each user, maybe around, they're releasing the rankings of 170 movies. The rating of 170. Okay. And what's our goal? The goal is, of course, as I said, to guess the missing entries. Okay. And so there's a data set, and then you get to propose a model. You get to, submit a matrix to them, and they'll give a score based on the average root mean squared error on some holdout entries. Okay, so even Netflix doesn't have all of the ratings, but when they release 1% of all data, they probably actually have 2% of the data. They had roughly 2%. They released 1% and said, okay, build your model and guess the other stuff. You don't know which 1% is missing, but they're going to score you on their values. And each proposal gets some score, and whichever kind of the best proposal gets some prize. Okay, is this setup clear? But they were actually a bit more, they were, I guess, maybe more pessimistic, I should say. They said, okay, we have a baseline model, and they gave a score for that. Their baseline model had something, you could see what it was doing, and it had some performance on the root mean squared error. I don't remember the exact number. I don't think it's important. But they said the challenge is the first team to do 10% better than their baseline gets 1 million. Okay, that was the prize money. If you bet their baseline thing by 10%, whichever was the first team to do it would get $1 million. Okay. I mean, this was in 2006, I think. So if you take inflation, that's quite a bit, right? Okay. Now, why am I talking about this challenge? Why is it connected to low rank approximation? Well, here's one approach you could try. So whenever you have such a challenge, such a question, right, you have to make some assumption about the truth. If you don't make any assumption about, how these sort of entries are related to each other, there's nothing you can do. Or you have to make some assumption about the underlying model. And one natural thing is to assume that the true matrix is kind of approximately low rank, right? Saying again, as I said, intuitively rank corresponds to having a small number of factors. Maybe the factors could be genre-based, maybe type-based, or maybe your own sort of education, geography, and all those things, right? But not that many of them. Okay, let's say I want to do that. As a, if you're analyzing the data, what would you do? Okay, let's say there's some miracle algorithm to solve the low rank approximation thing. Then what would you do? Or what could you do? Any suggestions? Well, low rank approximation seems very far from this problem, right? Because there are unknown entries here. Whereas in low rank approximation, you're saying I have a matrix, but I want to approximate it with a simpler one. So what's the connection potentially between this? Any suggestion? Well, okay, so first thing you might say is, okay, I'm going to pre-process the data so that, I center this course and normalize, just center this course really. Okay. Maybe a person likes every movie and, the entire row is all 5s. And there is someone who is very, very picky and their entire row is all 0s. Okay. Then it makes sense to kind of normalize by the average. Right? You do something kind of centering. Maybe you start with an even simpler centering where you just take the entire matrix, average it out, and then subtract that from every person so that you know kind of what's the median score. And then you get a sense of the preference or both, in comparison to the average ranking of a user across an average movie. Okay. And let's say the average turns out to be something, when you average it out, everything is in 0. The entries could be negative, like there's some things are -2, -1, and 2 and 3, and so on. What else could you do now? Once you average, what might be a good guess for the missing entry? If you center the score, what's a first cut guess for the missing entries? Any suggestion? Yeah. Exactly. Right. So essentially, you're saying as a first cut, I'm going to guess every missing entry with the global average across everything. If you don't want to do anything complicated, that's a reasonable thing to do, right? Okay. So put 0 for every missing entry. Okay, now we have an actual matrix X. You put in the stars are now gone. You have actual numerical values. But it's still, by putting zeros, you potentially made it much more complicated than the true matrix, right? So the statistical model, you could improve it further by looking at find the best low rank approximation x tilde to x. Maybe for some k, like, whatever k you choose, you do that. Okay. And what do you do finally? You just predict according to x tilde. Okay, you filled in the missing entries, but I'm not going to predict with the matrix with the missing and filled in entries, right? Because like I'm just predicting every person's value to just be the average. Okay. But if I do the best low rank approximation, it might do some better correction. That's the intuition. I put in zeros there, but it might figure out what the actual value is. And then I'm using that as a prediction. Okay, does the algorithm make sense? If you know low rank approximation, all you're doing is finding the best low rank approximation with the missing entries filled in with the average, and then using that as your predictor. All right. And one of the first things, once Netflix released the data set and everything, the cat is out of the bag, right? So you can try it out. And what happened? Well, people did this because low rank approximation is one of the oldest tricks in statistics for approximating matrices and matrix completion. And they observed that if you ran low rank approximation with roughly rank 30, you have a huge matrix. Again, as I said, 500K by 17K, just to give a sense of the numbers. To store 100 million entries, you basically, not the 100 million entries, but to store a 500K by 17K matrix, you need roughly 8 GB of RAM. Store matrix fully. Okay, if you don't have any sparsity or something, then you would need 8 GB of RAM to store such a big matrix, right? The dimensions are big, but they said, okay, I'm just going to use rank 30. Again, you try different things and then figure out what works best. And they realized that you bet their baseline by 4% already. So just using low rank approximation got you 4%, instead of being 10%, which was $1 million. Unfortunately, it wasn't scaling the threshold. It's not as if you just did this, you got 400K, but also kind of says like, they should have done this, right? Why would you not do it? It's kind of the first thing that people learn when you're doing low rank approximation, but somehow they miss the trick. Okay. So just doing low rank approximation did better than what they were, what they had. And once you got to 4%, people started with this as the baseline. Right? And then refine the low rank approximation technique using various ways to eventually get to 10%. Okay. So the problem of low rank approximation again is very nice one. Okay. All right. Now all of this is good, but how do you find the low rank approximation problem? Right? How do you solve the low rank approximation problem? How do you find the best low rank matrix? What does this have to do with the principal components or the best fit subspace problem that we're talking about? Okay. Luckily for us, something miraculous happens and there is a single solution to both problems. And this has been known for almost, 100 years or more. And that's the idea of singular value decomposition from numerical linear algebra. Okay. And it's a theorem. We're not going to prove it. It's a theorem from, as I said, numerical linear algebra from a long, long time ago. And it says the following. Right, if you've done linear algebra, you know that symmetric matrices have eigenvalue decomposition and things like that. Give you some nice ways to represent matrices. And singular value decomposition is something similar, but is applicable to any matrix. It can be rectangular, it can be square, it need not be symmetric, and is always there. Okay. And what's the singular value decomposition theorem say? If I have a matrix X or any matrix X, n by d, this is X, I can factor it as a product of three matrices. Okay, as a product of three matrices, this should be the same length here, U sigma V transpose. I'm writing it as V transpose because I want to think U and V both as tall matrices, right? So I'm writing X as a product of three matrices, U sigma V transpose. Okay, so if this is the only thing that you need, I could just write X as, X times identity times identity. Right? That's not very useful. But I want to do this with some special properties. The theorem is that any matrix X can be written as U sigma V transpose, where the following hold. The columns of U are orthonormal. Okay, meaning the columns of U each has norm exactly 1, and they're all perpendicular to each other. Okay, and algebraically, this is equivalent to saying U transpose U is actually the identity matrix, right? Because if I take U transpose U, then it looks something like this. I have R by N and N by R. I should get an R by R matrix. And it's orthonormal, meaning all of the cross products, inner products would be 0, right? So if we just get 1, 1, 1, 0, 0. Okay. And the same thing holds for V as well. Columns of V are also orthonormal. It's only when you put the two together that the condition becomes not true. Okay. Out of the three factors, U sigma V transpose, U and V are kind of nice matrices in the sense that their columns are perfectly orthonormal. Okay. And then, okay, how about sigma? It's an R by R matrix. It's a square matrix, and sigma is also actually very simple. In fact, sigma is a diagonal matrix. Whose diagonal entries are non-negative. Okay, so let me write it this way. Okay, sigma is a diagonal matrix, meaning all the off-diagonal entries are actually 0. The entries on the diagonal are restricted to be non-negative. Okay, that's the main theorem, that any matrix has a representation like this. It's like a non-trivial theorem, but we're going to just take it for granted and then work with it. Any questions about the statement of the theorem? All right. I should say that, sometimes I've written it as n times r by r, d. Sometimes you see it stated where in versions where the inner matrix sigma is full dimensional, like d by d and so on. But it doesn't matter. Everything comes out to be the same thing in the end. Okay. All right, let's just do a couple of examples to understand this. So let me say, okay, what if my X matrix is the following? What could be its singular value decomposition? If my matrix looks like this, what can be a singular value decomposition? In sessions? Yeah? Yeah, that works, right? So remember, all we need is the U part to be orthonormal columns, which is true for identity, and the sigma here is diagonal. Okay, good. Maybe that was an easy one. How about this? Let's say I have 1, 0, minus 2. Almost like the previous one, but now I have minus 2. What would be its singular value decomposition? Sessions. I can't use the same thing I did for the example 1 because sigma has to have non-negative entries. Okay, so what would be a singular value decomposition for this matrix? Sessions. Yeah. Yes. So basically, we just need to flip this 2, right? I'm going to put the negative sign here. It's not going to affect orthonormality, right? We just need the columns to be perpendicular to each other, and that's true still. And I can make this to be identity again. Okay, so this is U, this is sigma, and this is V transpose. Okay. And maybe let's say one final sort of simple case. X is an orthonormal matrix. So let's say X already has columns which are orthonormal. What would be an SVD then? Yeah. Yeah, X times identity works. All right. I mean, this is just a way to see that you get some nice properties. Okay. And why are we talking about singular value decomposition? Well, here's the magic. We say these are, we keep getting lucky once in a while in computer science. And there are 2 magical properties. So recall, we started out with the principal best fit subspace problem. That was a computational question. Given an input, a set of points, you had to find the best subspace. And then there was a low rank approximation problem. Given a matrix, find the best low rank approximation. And the SVD, as it turns out, solves both of them. Okay. Recall what the SVD says. I can write X as U times sigma times V transpose. Okay. So let us write it so that you order the entries of sigma. Yeah, so let's say these are U1 up to UR, and the entries of sigma on the diagonal are sigma 11, sigma 22, so on. Okay. Let me reorder things so that I satisfy this inequalities, meaning I'm writing sigma so that the largest entry is at the top right, topmost, top left. Okay. So in other words, instead of looking at something like this, let's say, I could also write it equivalently as, 0 minus 1, 1 0, 2 1 0 0. Okay. So this and this are equal. I'm just permuting the things. Okay. Okay, I can permute things so that this holds, and I'm permuting so that I have this set of inequalities. The largest one is at the top edge. All right. Now, I think I should have permitted this too. Okay. So under this assumption, the claim is that singular value decomposition solves everything. So let the rows of V be V1 through VR, of V transpose are V1 through VR, and the entries are in descending order. The first miracle is that when you do this, V1 is the first principal component of X. V1 is in fact the first principal component of X, and more generally, Vi is the ith principal component of the matrix X. Okay, you had a matrix, you found a factorization where of the form U sigma V transpose. You ordered the entries so that sigma is in decreasing order. Then the first k columns of V will solve the best fit subspace problem for K. In fact, the first one is the first principal component, the second one is the second principal component, and so on. Okay. That's the first miracle. This is, kind of nice, and it's a little bit easier, in fact, than showing the next one. Theorem 2, this is due to Eckart, Young, and Mirsky theorem from 1936. I said, these things have been around for a long time. And if you give me K and you ask me to find the best low rank approximation, the solution, as it turns out, is to basically look at the SVD and throw out all but the first K things. Okay. So maybe let me draw a picture. Okay. So the Eckart-Young-Mirsky theorem says if I want the best rank approximation, really only look at the first k columns of U, the k by k submatrix here, and the first k rows of this transpose matrix. Okay, you get a matrix of the form, right? Xk is basically U1, U2, all the way up to UK, right? And then I have the sigma, which I'm truncating, sigma 11, sigma 22, sigma kk. So this is an n by k matrix, k by k matrix, and then V1, so on up to Vk. Okay. Is a solution to the best rank k approximation. Okay. So if you could compute the SVD, you solve both the problems. The first k directions V1 through Vk give us the principal components and the span of the best fit subspace problem, and they are orthonormal, right? They're norm one, they're perpendicular to each other, so they give us a perfect, nice orthonormal basis for the best fit subspace problem. And if you wanted to find the best rank k approximation, all you have to do in some sense is compute the SVD, throw out all but the top k thing. Okay. So, we motivated best fit subspace, kind of nice question, many applications. Low rank approximation for matrix completion, it's a very, very nice technique. It has many other applications, not just for matrix completion. And both of them can be solved by SVD. Yeah. Yeah, so we'll get to that in a second, actually. Okay, so this, but at least now we can say both solve. I mean, we're really solving two problems in one go. If you could find the first principal components, they're also solving the low rank approximation problem. Okay, and you can also compute the SVD. But as I said, we've been kind of punting the problem down the line. So now we have to face the truth, and let's ask ourselves, how do you actually compute the SVD? And this is when you should ask the question that you asked, which is a very good one, right? What if I'm only interested in the first principal component, or I'm only interested in the best rank one approximation? Do I still need to compute the entire SVD and throw out the information? We'll see that you don't really have to. Okay. So in the remainder of today's lecture and the next lecture, we'll address this question: how do you actually compute the SVD? Right? We know that it's very useful. It solves both of these problems. How can we solve it? And then I'll also say a little bit about how low rank approximations and low rank matrices are kind of very useful in many, many sort of practical applications. Okay. All right, let's take a 5 minutes break, and when we come back, we'll start with trying to figure out an algorithm for computing SVD. How do you get the SVD? Okay. So before we start talking about the algorithm and how do you approach it, what are the nice properties that we need, let me use some tools, or let us figure out some other ways to look at SVD. Okay. And let me just say some properties of SVD. Okay. But I mean, without loss of generality, let's suppose that you are always writing it this way, where the entries of sigma are in descending order. Okay. Now, if I think of X, I'm writing it as U sigma V transpose, which is okay, so this is the U sigma V transpose thing. And instead of thinking of it always just as a product of three matrices, you can alternately also visualize it as the following. Because sigma is diagonal, when you look at this, when you're trying to expand this whole triple product, U1 will only be multiplied with V1 at all times. Okay, because sigma is diagonal, you don't have cross terms. So in fact, you can even write it as something like this. You can write it as a sum of rank 1 matrices, right? So U1 times V1 transpose, this is an n by d matrix, which is rank 1, right? Because I'm writing it as U times V, which is vectors. Okay. So these are n by r, r by r, r by d, and this is n by d. Okay, but this is rank 1. And so for actually developing an algorithm and deciding what to do with it, this view will turn out to be useful. Okay. And just for brevity, instead of writing sigma 1, sigma 2, sigma r, I'm just going to denote these things with little sigma 1. Okay. And this is called the first singular value, right? The largest entry is the first singular value. And this is the second singular value, and so on. Okay. So in other words, we just saying, what we just did was we can also write x as sigma 1 times U1 times V1 transpose plus sigma 2 times U2 times V2 transpose plus so on. Okay. We also gave some names to the V's, right? Because of this theorem, we know that each VI is the first principal component, and hence also the ith right singular vector, right? We said principal components are also called right singular vectors. And in the same way, we can actually call these UIs as first left singular vector. Okay, so U1 is the first singular vector, first left singular vector. U2 is the second left singular vector, and so on. Okay. All right. Now, the next property that we will use is some kind of equation. So essentially what we're going towards is in the singular value decomposition, there are three components. There's U, there's sigma, there's V, right? And what we'll see is that actually you don't need to know all three. If I know one, the other can be deduced or computed very, very easily. Okay. So in particular, the following holds. X times Vi is sigma I times Ui. Okay. So little, if you know what like in eigenvalues and eigenvectors, looks maybe a little bit like that. But remember, these are rectangular matrices, so they don't have eigenvectors. But X times Vi is sigma I times Ui. So there is this correspondence. If I apply X on Vi, you'll get Ui. Okay. Why is this? Well, let's just do some computation. We know that I can write X as sigma 1 U1 V1 transpose plus sigma 2 U2 V2 transpose plus so on. And I'm multiplying this with Vi. So what should happen when I do this multiplication? Any suggestions? Like, why would it simplify to something as nice as just sigma I times 2i? Yeah? Exactly, right? So, I have a sum and a product. I can push this product inside, okay? So I would get something like sigma 1 times U1 times V1 transpose Vi. Okay? And the same thing for sigma 2 times U2 times V2 transpose Vi plus so on. Okay. And since, the Vi's are orthonormal, Vj transpose Vi equals 0 if j is not equal to I is equal to 1 else, right? So only the ith term would survive and I would get sigma I times. Okay. Now in the same way, what happens if I multiply X with U on the left? What should I get? If I multiply with Vi on the left, I somehow only got the U. If I multiply with U on the left, what should happen? Something similar, right? You have these equations. If I multiply with Ui transpose, then all terms except the ith would vanish. Okay. So in particular, you get sigma I times Vi. Vi transpose. All right. Okay. Let me now ask you a question. If I tell you Vi is the ith singular vector, how can you compute the value of the ith singular value? If I gave you Vi, can you tell me what sigma I is? Little sigma I, the ith singular value. Yeah? Right. I mean, in fact, we don't even have to do that. Sorry, you're right. Multiply it, and then we know Ui is norm 1. Right? The UIs are orthonormal vectors. In particular, each one has norm 1. So sigma I is actually just norm of X times Vi. So if I know Vi, I just had to multiply it into the vector X, look at the length of the vector, it will tell me what little sigma I is. Okay. So as X times Vi equals sigma I times Ui, and Ui is a unit vector. All right. And so if I give you Vi, how can I find out Ui now? Well, this equation tells me how to find out UI, right? I just multiply with VI and then normalize it, right? So UI is actually X times VI divided by the length of X times. Okay. So this is just to say that if I know the V's, I can get the sigmas and the U's easily, and vice versa. If you knew the U's, also you can easily get the V's from this equation if you wanted. Okay.
So just to clarify here, like 4 and 5 U's and V's are interchangeable if both are orthogonal. Or is it not necessarily?
They're always orthonormal, but you know the multiplication has to be on the left or the right depending on whether you're working with U's or V's. Okay, so the dimensions are a little bit different, right? So kind of V's sit in the same space as the rows of X, and U's sit in the same space as the columns of X. Okay, apart from that, they're kind of very similar to each other. Okay, so let me just say, so in summary, if we know V's, we can infer sigma and the U's. Okay. All right. Now you might ask, how can I compute the singular value decomposition? And as it turns out, it's been extremely well studied. Almost every numerical software, NumPy, MATLAB, and all of those have inbuilt routines for SVD with massive optimizations built into it. And what we know is that I can compute the full SVD in time, which is O of ND squared. Okay. Assuming that you have a tall matrix, this is what you would use. Otherwise, you would use n squared times d. But you can compute the full SVD in time n times d squared. All right. So this looks very good. But then if you think of, let's say the use case of Netflix, it's 500K times 17K matrix. So this is N, this is D. ND squared is humongous. In fact, even ND is basically 8 GB of memory. So, this was a time when even now, 8 GB, 16 GB memory is not that easy, right? So even to load a big matrix like this is going to take up all of your RAM. Forget computing it. Not going to happen. Okay. Well, what's the saving grace? I mean, if you want to compute the full SVD, in fact, you cannot do better than ND squared. There's no way around it. Okay. But the saving grace is that you don't want the full SVD. It's a 17,000, 500,000 by 17,000 matrix. But as I said, people found out that you could 4% improvement just by doing the first top 30 rank approximation, right? So you only need to compute the first 30 singular vectors, okay? So question that we should ask ourselves is, can we compute first 30 singular vectors? Okay, can we compute the first singular vectors better than actually computing everything? Okay. So it turns out that you cannot compute it exactly, but you can approximate it fairly well. And that's what we're going to study. Okay. And you can approximate it quite well. And that's going to lead us to our next sort of powerful algorithm, which is power iteration. Okay. So in terms of algorithms, what have we seen, right? We saw gradient descent, we saw accelerated gradient descent, we saw stochastic gradient descent, we saw multiplicative weight method. And this is the fifth sort of algorithm that we're going to look at, which is power iteration. And its main purpose is to solve the singular value computation, singular vector computation. And as a result, both best fit subspace and the low rank approximation. And the punchline is we can approximate first. I'll do it for the first one and then we'll work towards more one. But first few singular vectors much faster than computing all. Okay. So what we'll do is go over the idea today, and then in the next class, we'll actually formalize it, see how well we do it, and then consider tweaks for it. All right. So to understand where this algorithm comes from, let's start with our reformulations, right? We said you have X, which is U sigma V transpose, but I can also conveniently break it down as the sum of this rank 1 matrices. Okay. Now we'll switch back and forth between the two. All right. So that's something that I want you to get a little comfortable with. Now let me define a new matrix, which is Y as X transpose times X. Okay, so for some strange reason that hopefully will become clear later, I'm multiplying X with itself. Right? So, well, what is X transpose? X transpose is U sigma V transpose whole transpose, and then you have U sigma V transpose. So this whole thing becomes V sigma U transpose times U sigma V transpose. I want to say I can simplify this much more. Why and how? Yeah. U transpose U is identity, right? So remember, we have associated here. You're multiplying a bunch of matrices. The order is important, but the way you kind of group them isn't important, right? So I can group these two together first, and we have orthonormality of the columns of U, which we said as a result means that you have identity here, and then sigma times V transpose. So U transpose U is identity. So this whole thing simplifies as V sigma squared V transpose. Okay. Well, we did something, at least we got rid of the U's. As I said, instead of figuring out all three components at once, we'll figure out one, and once we know one, we can deduce the others by using the equations that we had, right? Now, if I have Y, what about doing the same thing again? What is Y squared? Well, let's figure out what are the dimensions of this, right? So V is a D by R matrix. Sigma squared is, still R by R. V transpose is a R by D matrix. Okay. So Y is actually the D by D matrix. Okay. It's sometimes also called the correlation matrix because you're just looking at the correlation of the different rows of X with each other. You have your data set X1 through Xn, and you're somehow looking at the correlations across dimensions. Okay, so that is good. It's a square matrix. What is y squared equals y times y. I can use the same expansion again. So you have v sigma squared v transpose times v sigma squared v transpose. Can I simplify this further? Yeah. Yeah, because v transpose v is identity again, right? So I get v sigma to the 4 v transpose as v transpose v is identity. Okay, so you get the drift now. What about y cubed? What should I get? Yeah. Yeah, v sigma to the 6 times v transpose, right? So if I keep repeating this, I do this maybe L times, then I get this identity. Y to the L is v sigma to the 2L times v transpose. Okay. So y was v sigma squared, y squared is y sigma to the 4, y cubed is y sigma to the 6, and so on. Okay. Well, good. Now another question. What is sigma to the 2L? We call sigma was a diagonal matrix, right? So sigma was, oops. So this was sigma, right? You had a diagonal matrix where the entries are something like this. And what can you tell me about sigma to the 2L? Yeah. Right. So when I multiply a diagonal matrix with itself, the entries just get squared, right? So this also has kind of a nice form. In particular, the new matrices are also diagonal. Okay. So if I multiply sigma with itself, I'll just get sigma 1 squared, sigma 2 squared up to sigma r squared. The off diagonals will still be 0. And in general, I will get something like this. All right. So what does this mean? I can write y to the L as you have v1, v2, up to vr. This is v. Then we have sigma 1 to the 2L, sigma 2 to the 2L, sigma r to the 2L, which is sigma to the 2L, and then the transpose. Oops. Okay. And as I said, when you have a diagonal matrix sitting in between, this V1 is only going to interact with the first row here, right? The first column will only interact with the first row. So just as we did before, I can also view it as a sum of simple rank 1 matrices, just V1 times V1 transpose plus V2 times V2 transpose plus so on, right? So in particular, y to the L is just sigma 1 to the 2L times V1 transpose plus sigma 2 to the 2L times V2 transpose plus sigma r to the 2L times VR transpose. Okay. All right, we have some equation, we did some arithmetic, we did some matrix manipulations, and we got this identity. Why is this useful? Why am I doing all of this? Well, let's do like a thought experiment, right? What do we know about the sigma i's? Their powers, the sigma 1 is the largest of all of them, right? When I have sigma 1 is bigger than sigma 2 and so on, if I raise them to higher powers, what should happen? The gaps become bigger, right? They become bigger, but the gaps become even bigger, right? So for example, as an example, just to scale things somewhat, suppose sigma 1 was 1. I'm just normalizing that sigma 1 is some number like 1, and maybe sigma 2 was like maybe 0.8, right? And then sigma 3 and so on, they're all smaller, even smaller than 0.8, right? Now, when you raise to higher and higher powers, what happens, right? These things are decaying exponentially compared to the first term, right? So y to the L is something like 1 times V1 transpose plus 0.8 raised to the power L times V2 transpose, and plus some other stuff where the numbers sitting in front of them, they're all going rapidly to 0. Right? So all of these things, as you increase L, they're going to 0, whereas this one is standing out. Okay. So in particular, you can imagine that as L becomes larger and larger, as you take L to going to infinity, what should happen to y to the L? Yeah. Just the first one, right? All of these things are decaying. In fact, we don't have to go to infinity. They decay exponentially, right? So they'll become small pretty fast. Okay. So at some point, y to the L will essentially look like, oops. So y to the L will go to V1 transpose. So in particular, what is this matrix? You have V1 and you have V1 transpose, right? So why is this a good thing? We don't know what V1 is, but we know what Y is. Y was just XX transpose, right? We multiplied, we are given the matrix X, and we had to compute the first singular vector or V1, right? So we said, okay, I don't know what V1 is. I'm just going to manipulate X somehow. I'm multiplying X transpose with itself. I got Y, and then I'm multiplying Y with itself again and again. Let's worry about efficiency later on. But when I do this, I'm getting this matrix Y to the L. And the good thing now is that the rows, it's a rank 1 matrix, V1 transpose, right? If I give you this matrix, how can you read out V1? Any suggestions? How can I read out V1 given V1 transpose? Yeah. Right, but then you might miss the sign, right? But right, so actually you can just look at the first column, right? Even if I look at the first column, what is this matrix? The first column is basically V1 times a number, right? All of the columns are all proportional to V1. Right, the first column is some number times V1. The second column is some number times V1 and so on. Okay. So if we look at the first column of y to the L and normalize it, meaning make its length 1. Okay. Then we should get V1. Right? For some sufficiently large power, we can keep doing this, and then we would be good. Okay. So as a method of approximation, here's a reasonable sort of algorithm, right? So the idea one, compute y to the L for some large L, like let's say 100. And I'm going to compute y to the L for 100, and then I have like this 0.8 to the power 200, which is like really small, right? It's going to shoot past the floating point arithmetic precision pretty soon. Okay. And then I compute the first column of y to the L, right? In fact, all I need from y to the L is not the entire matrix, but just the first column. That gives me V bar. Let me call this V bar. And then I say, as my approximation for the first singular vector, I'm going to output. I need to output a unit vector. V bar need not be unit vector, so I'm just going to normalize it to have length. Okay, very good. Now I want to do one twist to this, and this will lead to essentially the power iteration algorithm, right? Can you tell me this one source of inefficiency here? Yeah. Matrix multiplication, right? Does it seem avoidable? I mean, doesn't seem avoidable, right? If I had to compute y to the 100, I have to multiply y times y, right? But what's happening in the second line? Do you really need to compute y to the L? What do you need to compute? Only the first column of y to the L. But it seems like chicken and egg, right? I want to compute the first column of the 100th power of y. But how can I do that without computing, like, let's say the 99th power of y fully? Right? Well, I think that's why like matrix notation is actually beautiful, because it just tells you the answer. This is y to the L. I can write down the first column as a matrix vector product. What's the first column? If I want to write it as a matrix vector product, what should I multiply with on the right? Yeah, the first basis vector. So consider putting something like this, right? So what I really need is not y to the L, but y to the L times the vector which has 1 in the first entry and zeros everywhere else. Okay. Now, why is this good? Why is looking at matrix vector product better than multiplying the matrix again and again? Yeah, can go backwards, right? You never have to compute matrix products, because that would be really expensive, right? So what would you do? I would say, I'm going to write y to the L as something like this, L times, and this is what I have, right? But I'm not going to do the multiplication in that order. I'm going to do it in this order. Okay. All right, this is much better because you're never multiplying a matrix with itself. We saw in the assignment that it's super expensive. It's ND squared time, whereas matrix vector multiplication can be much faster, especially if you have additional properties of the matrices. Okay. And basically, this is essentially power iteration, right? And a succinct way to write it is as follows. I start with some vector I'll call V0 bar, which is 1 and all zeros. Okay. And then I'm going to do this L times. What am I going to do? I'm going to multiply my vector with y L times. Right, so I'll say VT bar is y times VT minus 1 bar. Okay, that's just the same powering operation, but just kind of unfolding it from right to left. Right? And finally, I had to normalize. So output okay, this is power iteration. So this is the algorithm that we're going to study in next lecture. We'll tweak it a little bit further for computational efficiency and some precision issues later on. Okay. All right. So we'll talk about this and its properties and what it says about singular value decomposition next lecture. Right. Okay.